So once we have a discrete random variable, as we discussed in the previous subsection, subsection 5.1, we now want to know the probability that our random variable could take different values. And we can do that through something called the probability mass function, or the PMF. So the idea here is that for any set A, we can work out the event that our random variable is in that set A just by adding up all the individual probabilities. Because for a discrete random variable, everything's countable, so we can use axiom 3 to add up the probabilities. But this means that kind of all we need to know is this probability that capital X equals little x. And we can encapsulate that in something called the probability mass function. You write P with an X subscript of X for the probability X equals X. And that's called a probability mass function, or PMF for short. And I will use the abbreviation PMF a lot, or a probability mass function. Also, you see that subscript capital X. When it's obvious what random variable we're talking about, then we won't bother writing that capital X. But if it's not totally obvious what random variable we talk about, it's useful to put that capital X down there just to make it clear. So this probability mass function just tells us the probability our random variable takes different values. And the good news is that once we've got a random variable and its PMF, its probability mass function, at that point we can kind of stop thinking about sample spaces and sample outcomes and what's capital omega and how should I write my events in set notation. Because at that point we can just think about our random variable. We don't have to think of all the other technical stuff in the background. And that will make things much easier and much more pleasant for us. So let's think of the example of rolling 2 dice and looking at the total, which we looked at in subsection 5.1. So here's an example. If X is the sum of 2 dice rolls, then we know that the probability of rolling, the total X, well, this is a classical probability, so it's something over 36. And on the top, we've got kind of a number of ways of rolling X. So, for example, the number of ways of rolling a 2, well, there's only one way of rolling a 2, right? You have to roll a 1, then another 1. But rolling a total of 6, for example, there's quite a lot of ways you can roll a 6. You can have 1 and 5, you can have 2 and 4, you can have 3, then 3. You can have 4 with the first dice and 2 with the second, or 5 with the second dice and 1 with the first. So that's 5 different ways. And if you work all those out, you'll find it goes 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. And so you can write out the probability mass function. So X takes the possible values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the probability mass function, P of X, takes on values 1 over 36, 2 over 36, and so on. So that's the probability mass function of the dice roll. The probability mass function simply tells us the probability of getting those outcomes. Here's another important example. Suppose we toss a biased coin that comes up heads with probability P and tails with probability 1 minus P. So we're tossing a biased coin, heads with probability, WP with probability P, and tails with probability 1 minus P. And our random variable we'll count it as 1 if we get heads and 0 if we get tails. So X equals 1 if we get heads, or x equals 0 if we get tails. So then, for this, we have the probability mass function is p0 equals 1 minus p, because that's the probability we get tails, and so our random variable counts 0. And we have p1 equals p, because that's the probability that our coin lands heads, and we count 1. So it turns out that this is quite an important type of random variable that comes up a lot. This is called a Bernoulli Trial. Bernoulli Trial. Or a Bernoulli distribution, or a Bernoulli random variable, or something attached with the word Bernoulli. And that refers to this. Here we thought of it as tossing a coin, but you could equally well think of this as, it's an experiment where you succeed with probability p and a success counts 1, and you fail with probability 1 minus p and a failure counts 0. So this Bernoulli trial is a type of random variable we'll see quite a few times later on in the course. There are some facts that we should point out about the probability mass function. If you add up all the values of the probability mass function, well, that's the probability of getting anything at all, right? And we've spoken before about how the probability of getting anything at all is 1. So PMF's sum to 1 is important. Also, of course, all the individual values of a PMF are probabilities, so they all have to be positive. All x, so PMFs are non-negative. They can be 0, but can't be negative. Otherwise, they have to be positive. So those are two useful facts to remember about probability mass functions. So the probability mass function tells us what's the probability we get some value exactly. We might also be interested in what's the probability our random variable is less than or equal to something. So rather than what's the probability we hit a certain value dead on, what's the probability that when I roll my dice, I get no more than 8? That sort of thing. So we might be interested in that as well. And we can talk about that through something that's called the cumulative. Cumulative kind of means up to distribution function. Or CDF, again, another abbreviation I will use a lot is CDF, cumulative distribution function. And this is capital F being the probability that the random variable is less than or equal to some value for any real number x. So rather than the PMF tells us what's the probability we get certain values, cumulative distribution is what's the probability we're up to some value. And so hopefully it should be clear that we can get this by adding up the PMF of all the smaller values, right? So this is kind of the sum of all the values up to x of the PMF. Because if we're smaller than x, we must have taken one of those smaller values, and so if we add up all their PMFs, we get the value. So we can work out what they are for our examples as well. So for the Bernoulli trial, and when we're doing a Bernoulli trial, we sometimes write it like this: x, and that's a twiddly line, like a tilde, a little twiddly line. Bern, short for Bernoulli. P, meaning P is the success probability. So the CDF is, well, the Bernoulli random variable can only take 0 or 1. So if x is less than 0, it's impossible for the value to be smaller. So that's a 0. Right? Similarly, if x is greater than or equal to 1, well, you're certain to be less than x because you can only take values 0 and 1. So what's the probability you're less than or equal to 3? Well, it's certain. And then in between 0 and 1, although the probability we're less than, say, a half is the probability we equal 0, because 0 and 1 are the only possibilities. So this will come up as 1 minus p. So notice that we have this kind of behavior for different cases, where the CDF is flat, then it increases at 0, it's flat again, then it increases again at 1, and it's flat at the top. Similarly, we can do the same for the total of the dice rolls. I won't write out the whole thing, but again, you have this kind of stepwise behavior. If f is in, I'm using that set theory notation for is in. So if you're between minus infinity and the smallest possible value, smallest possible total is 2, then there's 0 probability. On the other hand, for values between 2, including 2, and 3, but not including 3, the only way that can happen is if you get a 2, so that's 1/36. Between 3 and 4, you have to get either a 2 or a 3, so that's 1/36 plus 2/36. And so on, all the way up to the probability of being less than or equal to, say, 11.5 is anything except a double 6. And then above 12, you're certain. So again, you have this kind of stepwise behavior where at each of the possible outcomes, you increase a bit and then go flat. There's a picture of what the CDF looks like that in the notes if you want to see it. We can also mention a few facts about the CDF as well, which is if x is lower than everything in the range, well, then the little x is lower than everything possible. So it must be that the cumulative distribution function is equal to 0, because that's the probability that x is less than something that we know it's always bigger than. And similarly, if x is higher than everything in range x, for the same reason f of x must be equal to 1, because you're certain to be less than or equal to that thing because it's bigger than the whole range of possible outcomes. Also, we notice that f of x is increasing in x, because as x gets bigger, the probability that you're less than that value becomes more and more likely. And so if you look at this example here, it goes 1/36, 3/36, all the way up to 35/36, and the Bernoulli case always increases as well. So those are some facts about the cumulative distribution, to go with the facts we saw a few minutes ago about the probability mass function. And learning to use the PMF and the CDF will be important when we're looking at discrete random variables.